Today we're going to be showing our PLR technology. PLR stands for Part Localization in Racks. So this is a purpose-built system. It is designed specifically for deracking applications. So today we're going to walk through how to integrate it into a FANUC robot, actually program it, and how to actually run it. We're going to go through a full mini application using our demo system that you should be able to see on our screen here. This is going to be broken into 3 different sections. The first is going to be a system overview. This is just all about the PLR. What is it? What am I talking about when I'm talking about deracking? Any of that kind of stuff. After that, we're going to look at the system integration into a FANUC robot. That's what we have here on the screen. We can, just for your knowledge, integrate into any robot. It's just TCP/IP communication. So any robot is possible. FANUC is just what we're using today. And lastly, we're going to go into the job configuration, which is actually setting up the PLR device and using it to pick apart. System overview, PLR. This is what a PLR device looks like. It's what you should see on your screen. It's what you should see on the video. This is what comes as part of the package. There's the illumination up top. We have a big LED illumination that's going to help you drown out ambient light. We have a 2D camera inside. That's the camera opener. There's an SD card slot, and then there's a laser cross that can be projected. In addition, this can be daisy chained, along with it's a 5-pin daisy chained Ethernet, and it's a 5-pin 24-volt connection. Takes about 1.3 amps. So this is the typical architecture of a system that uses PLR. The PLR device is going to either go straight to your robot, or it can go to a switch and then go to your robot. The PLR device is a smart camera, so it does have a web server. You do not need an external PC in order to use it in production. You will need some sort of laptop or some sort of HTML5 browser to be able to configure it. But after that, it's good to go on its own. You don't have to have a laptop constantly hooked up to it. So again, it is a configuration via a web browser. So nothing too difficult. It's very purpose-built. So there are features in there, but we're looking at strictly deracking when we're looking at this system. So the device. Essentially, what it will do is it's going to take an image. It's going to take 2 different images. The first image is going to use some sort of features to look for your X, Y, and roll, just like a regular 2D camera. So you'll need some features that can support that. Then it will take a second image, except for this time it's going to display a X in the form of an LED cross on the part. You will need a 40 by 40 flat surface, millimeter flat surface, to be able to do that. From that cross, it's going to look at the angles, which will give it the yaw and pitch. It'll measure those angles, and then it's going to look at the axial location of the center of the cross relative to the camera's axis. That will give it its Z offset. The camera, we have 2 different versions. One version is a 365 millimeter standoff, so you want to be 365 millimeters from your part, or the other one is 230 millimeters from your part. There is a minus 100 millimeter and plus 150 millimeter range from that standoff location. Accuracy-wise, those 2 have a slight difference. The shorter range version is going to be slightly more accurate at 0.5 millimeters in your XYZ, whereas the longer range will be 0.8 millimeters in your XYZ. And the measurement time is very quick, normally at 0.5 seconds. This particular one you'll see today, I have clocking in at about 0.3531, something around there, so very quick. So again, you're going to take this image, there's going to be a cross, everything in the field of view, which is 260 millimeters by 260 millimeters. You're going to get a 40 by 40 flat surface, and you're going to need some sort of edge features to be able to find to create that XY roll. Here are some general ideas of what a typical application would look like. You're looking at a door, and you're going to be some sort of reference. That reference is going to be what you teach to. So that's what your robot points will be expressed in. That's what the PLR will know. That's where your reference is set up. Then you're going to be able to shift really anywhere you want as long as those features are able to stay in the field of view. Same goes for this tilt. This is how the tilt works. Again, you'll have some sort of flat surface. You'll have this X on there. Then it's going to be able to tilt, and that's how the PLR is going to measure your tilt, skew, and distance. Again, we have integrated illumination. The illumination is that big top light bar. The idea is that we're able to drown out ambient light. Ambient light's going to mess with any vision system. It doesn't matter whose you're using. So our goal here is basically make a binary image. We want to drown out everything in our surroundings, and we're going to create a reflection, which will give us a nice binary image where we get heavy contrast. That's going to give us a very reliable system. That's part of the reason why we're so close to it at that 360 millimeter standoff. So one problem that you can run into with the PLR is you have only a 260 millimeter by 260 millimeter field of view. That's not very big in a lot of applications. So we developed with some of our other technologies what we call PLF. What PLF is fusion. So we actually make a fusion of the PLR device and one of our 2D sensors called a Plock 2D. That way you can use the PLR to get certain features, maybe just the cross, and then you can use the 2D camera at a different location to get your XY roll, or just your X, or just your Y, any of that, but you can split up the what's measuring what, which allows you to have a much easier time focusing on your part. You don't have to have a part that's very specific anymore. This PLF runs in the background. It's not something that will look any different to your robot. It won't look any different to you. Essentially, it's just an app. It uses our app space. Our app space is a newer thing here, but it's an app space program that combines the two in the background, and it acts as just one PLR. And this is kind of an example of what it looks like, where you merge the information. So in this case, the PLR is getting your Y, Z, then yaw, pitch, and roll, while the Plock 2D on the side of this hood is able to get your X, and it's helping with the roll because it's getting the X. And they're split up on the device. Again, it's very quick. This will be done within 0.5 seconds, but it's much more robust when you have a surface that's not quite as featured here. This also can be mounted on the robot or off the robot. It does not have to be on the robot, even though that's what we're showing today. So differences between PLR and other things. The PLR is a relative position offset. It is not an absolute position. So when we're using it, essentially the absolute positioning would mean that with the robot, we're getting a point. We go exactly to that point. The robot's coordinate system is matched up with the camera coordinate system, and that point is a specific target in our field of view, in our work frame. In the case of our bin picking software, which is PLB, that's what we use. We have some sort of absolute positioning. We align the camera with the robot's coordinate system, and we can go ahead and pick directly to that point. In the case of the PLR, we are using relative position offsets. So what this means is it's more of we have a taught reference, and then we're using some sort of calculation to be relative to that taught reference when we're doing the pick points. In the case of the PLR, this exists as a frame offset. It's not like a 2D camera where you just have your X, Y, and roll, and then you can just minus or add it to your reference. We're actually going to be, and I'll show you this later, doing a matrix multiplication. So again, differences between absolute. We're not coming right off the coordinate frame. We're going from a reference point and then using a relative transformation from there. So this is how the PLR works. Once we have set it up, work through everything, we're going to have a taught position. That taught position is where we're going to take our first measurement most of the time. You could, depending on your application, do this different ways, but your first measurement will either be right at the taught position, it can be indexed in, or it can be based on your last pick point. So it really depends on your application, but you'll take a first measurement. And if the part is really tilted and it's not quite going to give you the accuracy, and there's a parameter in the system for this, but if it's not quite going to give you the accuracy you want, it's actually going to do a reposition. That's that second measurement we're showing here. So the system can actually say, okay, I'm not going to have the accuracy that you want, so we're going to reposition real quick here, and we're going to take a second snapshot in order to get the accuracy that you want for this application. So that's very robust in terms of what we're doing. All right. So integration, we're going to get into some of the fun stuff. I hope I didn't bore you guys too much there. So when we're jumping in here, TCP/IP over Ethernet. So we are just doing socket messaging. The PLR can support XML and CSV. It will automatically determine what you're sending it. We do give you guys the templates, not something you guys have to develop on your own. We have developed them over the years, and they are free on our support portal. We have templates right now for ABB, KUKA, FANUC, UR, a whole bunch of others. There's tons of them out there, but this one again will be FANUC in this case. On a FANUC robot, we typically need for options, it will be the user socket messaging option and the Carol option. Different robots are going to be different options. For FANUC, that's what we're using. When the system runs, the robot is going to send a request to the PLR. The PLR will perform an operation, and then the PLR will send back to the robot. It's the only way the PLR operates. The PLR will never send something to your robot first. The robot is the master of the system. It is going to be the one communicating first and then receiving something back. So this is what the command structure looks like for the PLR system. There aren't that many commands. First, we have alignment. So that's when we want to align our system with the robot's tool center point, which we'll get to later. We have job teaching, and we have run. There are functions as well to restart the system if you need to, along with exporting your images via FTP to some sort of server or anything else. Coming back from the camera, the important one to know here is the C transform in green. The C transform is our correction frame. That's the one we actually use when we are multiplying our matrices for our offset position. Our other transforms give you other information. So if, say, you wanted to create boundaries where you didn't want to go out of, you could use one of those transforms to see how far you are from the reference point and use that to create a boundary in your robot program. So many different things you can do with these. It's really as much as you want or as little as you want. So I'm going to switch screens here, and I'm going to show you guys what this looks like on the robot side. One moment. All right, so here I have a echo of my robot. So you guys should be able to see this point. And so I'm going to show you guys exactly what we've done. Again, this is written in Carol, a lot of this background code. It's code we give you guys. We'll give you the source. If you want to edit it, you can. If you don't, we also have other ways of doing it through XML. When you actually start the robot, we're going to be looking at what we call PLR com as the program. Once we move down here, it's very simple to set up. We're going to first parameterize our program. First AR here that we're putting in is the digital out that we're using to say the system is online. So when we start the program up to try to communicate, this is the DO that's going to turn on when we're good to go. Second parameter here is our client number. I'll show you that in a moment. Just real quick, setting up a client within the robot, not very difficult. In this case, I'm using client number 2 as the PLR's client number. We have a port number. That port number can be set on the PLR side. Not very difficult, but I'm using port 14158. That is the default port on this device. Again, it can be changed. Lastly, I'm telling it where I want the information to be put. So I have quite a bit of information that's going to come from this PLR device. and some of it is in the form of registers, and some of it is in the form of position registers. So I have it starting at number 70 for the registers and number 82 for the position registers. So if I show you where that is, you'll be able to see we have a whole bunch of different through here. Our process code is actually part of the Carol program. The process code is basically what's going on. 1 means it's received a command from the robot. 2 means it's sent, it's built the message and it's sending it. 3 means it's waiting on the PLR. And then 4 means it's gotten the message back and it's processed it and it's ready to go. Com status, if it's a 1, we're communicating with the PLR. Those are all both internal to Carol. That's part of our Carol program. Last few here are part of the actual PLR interface. So what the PLR reports back. There's a lot of information, a lot of things you can do with it. Again, this is all in the manual. It's something that you'll have to decide what you want or don't want to do with. So if we go to the position registers, again, these are at 82. We just have those frames that it's just these 4 frames here, D, correction, and F and T. Those are the only position registers it's going to send back to me. My other things here are parts of my program, which we'll go through later. Lastly, when I want to go set up a client, what I do is go to my host communication. I'm going to go to my TCP IP, and I'll set up my IP address, which in this case is 192.168.120. Default is actually 192.168.0.1. I've changed it in this case. So I'm going to set it up here, and then I'm going to go back. I'm going to go show, and I'm going to show my clients. I'm using client 2 in this case, detail, and I'm going to define that I want to use PLR as my startup, and I'm going to set the start when the robot starts. So that easy. That's all we have to do to get the system communicating. So once we go back here, these are just my parameters that I've set up then. I'm going to run this PLR PRM. That'll set the parameters in the Carol system. And then I'm going to run this in the background. This PLR SM is the actual master program that's going to do all the horse trading between the PLR and the robot. I'll wait for my communications to go online, and then I'm good to go. That's all I got to do. So not rocket science, very easy. We give you guys all the code to do this. It's not something you have to do on your own. It's something you're absolutely welcome to do on your own if you want. All right. So from there, installation job configuration. Drop down here. So the first thing we're going to do when we have a PLR application is we need to align the camera with the robot's tool center point. So that means that I've already taken a tool center point with the robot. I have my tooling installed, my tool center points in the robot system. I don't need a tool center point for the PLR. The PLR is just going to find its location relative to my tool center point in the robot. And so I'm going to move this robot over, and I need to get my video. One moment. So I need to move it over, and I'm going to set up that ability to go ahead and align. And so when we do alignment here, we're going to be looking at a frame just like this. So you'll have it installed. You'll have an alignment frame here. This alignment frame is how the PLR will understand where the tool center point of your robot is. So what will happen is we're going to take a user frame on A, that'll be our origin. Our B is our plus X, and our C is our plus Y. That user frame will then be a common frame between the PLR, because it can take a picture of this alignment frame, and the robot's tool center point. We'll express the tool center point in that coordinate system to the PLR. From there, it can basically say, I know I'm this far from the frame. If I'm this far and it's being reported as this, math, here I am, here is my location relative to the tool center point of the robot. That's how we end up getting our end result. All right, so I'm gonna go ahead and move this over. So again, A will be my origin, B is my positive X, C is my positive Y. This robot you should be able to see on your video feed here is going to be coming over a little slowly here. I'm running it in manual. Over, and it's going to take an image of this this frame here, this grid. So when it's up here, what's going to happen is it's going to take that image. It's going to take about 10 seconds for the PLR to process. This is only has to happen once. You can run a verify. And so you just saw it's going to reposition itself. When it does that reposition, that's basically the PLR saying, okay, I know where I am. It'll be a little bit different to get a better image. So I'm going to bring up the PLR feed here so you guys can see a little bit more of what's going on there. When I run into this PLR device, again, it is a web interface. It starts up in run. I'm going to change it to maintenance mode. And that actually unlocks my alignment. So I'm going to bring this back over. Now you guys have seen what this looks like. Also, if you see, I have this device up on a 90-degree angle right now. That's not necessary. You can actually rotate the PLR 90 degrees any which way you want. It just has to be at some 90-degree angle, parallel angle to the grid. So when it takes an image here, I can actually run continuous. And you'll see this is what the PLR is seeing at the moment. I can go into an installation tab and start to work with my my exposure time and my contrast to try and get a better image, if that's what I would like to do. Again, I'm already set this. I know my exposure is good. We do have other ways of helping in this case. The alignment aiming laser, something I can turn on. Same with the laser cross. When I turn those on, there's 2 dots from the aiming laser, and there's a cross that comes out for the laser cross. If I line those up, I'm at my standoff. So when I set this up, that's the first thing I'm going to do is I'm going to turn those on. I'm going to look at my video feed, or in this case, I can look at the robot. And as long as those dots are aligned with my cross, I know that I'm at the standoff. Go ahead and turn those off. So at that point, I have actually made my point here with my robot. I know exactly where I want to be to take this first image. I'm close enough that I can see the whole grid inside my field of view. The alignment tab, again, something we can run here. If I go ahead and run the PLR again, see the system, go ahead and update. Take an image. See this image, again, take about 10 seconds to do calculations. And it's going to take another image after it repositions. I'll run through that again. So if you see reposition according to the suggestion below, that suggestion was sent to the robot over the TCP/IP communication. Now my alignment was successful. So how is that done on the robot side? We'll jump through here again. So when I run through PLR alignment, so here's my COM. That was what we saw before. That's how I actually get online with my PLR. From there, I'm going to go to a position register. That's my reference point. I've taken this reference point manually, saying that, hey, here's my field of view. I know that it's in the field of view at this point. And I'm going to set to U frame number 9. 9 is what I took as my user frame for this grid. So I'm going to send the command, and I'm going to wait for a response. My command here is align, and I'm using my alignment profile 1. That sends a command over the TCP/IP interface. That command is alignment.align, along with some other data about the robot's tool center point. From there, we're going to wait for it to respond. When it responds, we're going to see if there were any errors. If there weren't, we'll continue. And do we need to reposition? You saw that in this case, it did reposition. So if it did jump down to label number 10 here, if it didn't need to reposition, we'd just be done. We would finish. When we do reposition, what happens is the PLR again reports a frame offset. So I'm going to take the frame that I'm using, which is frame number 9. So we have data within that frame. I'm going to go to that. In my user frames, my frame number 9, this is my data. Let's go here. This is my data for that alignment grid that's on the wall in my office here. And so I'm going to take that and I'm going to multiply it, do a matrix multiplication. And again, this is done in Carol here. This is a Carol program. You can get an option from Fanuc that allows you to do on the TeachPen side, but we can also give you the Carol version. That way you don't have to buy an option for it. But we're going to multiply that frame number 9 by reference position number 83. The C coordinate transform that PLR is giving back to us. So again, that is over here. That's the correction frame, and it's also got information. When I matrix multiply those two together, I'm telling the system to put it into reference position 87. That will give me the corrected frame. From there, I'm going to move in my corrected frame to the same point. So that same reference point, my PLR align point that I started at all the way back up here, PLR align, I'm going to move to that same point, except for I'm going to do it a temporary frame where I have set up this calculation. That will allow me to use the offset because I'm now in a different frame of reference. My coordinate system is different. So moving to that point in a different frame gets me to the offset. So sounds complicated, it's really not. It's really easy once you run this program. It does most of the work for you. So that's how it's set up. That's how it's working in this case. So at this point, I am aligned. The system is showing me if you see all these little blue dots, it's showing me the coordinate system that's working with. I have aligned the system. The PLR knows now where the tool center point is relative to its location. And so when it comes to alignment, it's something that you only need to do once if nothing moves. So if you don't have anything hitting your robot, you don't have your PLR device move, your gripper or your suction cup that doesn't move, as long as everything is rigid, you never have to do it again. If you ever want to check it, we do have a function called alignment verify. So you can actually bring it over, take a picture of this as long as this has not moved. So generally you'll want this grid as a permanent fixture somewhere in your cell. But as long as it has not moved, you still have a good user frame on it. You can come around, take a picture. That picture will be the quick type. That'll be that 0.3 to 0.5 seconds. And you'll be done. It'll tell you, do you need to align? Do you not need to align? And so you can give a nice quick, good to go. And if you don't, then you can run the alignment, which is about, again, 10 seconds. It's not very long. So it's a very good error proofing mechanism. If you have maintenance going on or anything else, it's all very good for that sort of error proofing, making sure that, or trying to get something back up really quickly. So from here, going to run into the, I'm going to give you guys a little run through of the actual interface here. And then we're going to look at an actual job setup. We only have 5 tabs. The first tab, again, is installation. We're just really looking to play around with our exposure time, our contrast, our position offsets. Nothing really special here. It's really just to be able to play with the device without impacting anything else in the system. Again, alignment, you've already seen. Job, the job screen here. This will be for things I've already set up at the moment. We're going to work with job 2 though. And job gives us a good bit of things to work on once we get there. Run is actually our run screen. So when I want to run a job, you can go into here and just watch it. You can also manually trigger it to see what it's going to be doing. And lastly, we have system. This is where we're going to set our IP address. We're going to set up our FTP, any port designations, anything else. So we also have a nice system log here. So if it does save quite a bit of data. If you need to do any sort of service, figure out what happened, you can save this out and be able to see what the robot was sending, what the PLR was doing, and work on your application. All right, that's everything there. Once we get into a job though, I'm gonna jump back over here. Managing jobs. So we're able to load and save jobs. The system has 9 jobs internally that you can work between. I believe it can have up to 68 jobs or 64 jobs, my bad. The first thing we're going to do is grab a reference image. When we move over to our part, we're going to adjust some image properties. So we'll change some of the features that we're looking at. We're going to change any of the reposition thresholds, anything like that. But the main idea here is to maximize the contrast between our features and the background. We're looking to create a binary image as much as possible. So this is what a typical application looks like. Again, you need a 40 by 40 flat surface. You're going to approximately need to know the part's position beforehand. Again, that's a -100 plus 150 range. Your goal is generally to get this X within your field of view to start with, but if it's not there, we do default to scale and reposition. So it's not absolutely necessary. It's just, it makes your application work better if you can get close the first time. Again, some more examples of how this will work, the type of features it's going to pick up. So we have a bunch of different ways of doing things. Again, it works for many, many different applications. It picks off of racks. Everything you see here is all about deracking. It's a purpose-built device and it's meant to be simple. So go back over here. All right, so I'm gonna show you guys how simple this is. Again, the idea here is this is a purpose-built device. There's no special tools you have to do. It pulls in everything for you. It is just meant for deracking. So when I just erased, it's going to unload some of this data here. Oh, it's not updating. Reconfiguring the job. It's taking a couple seconds here. Regardless though. So I'm going to be able to teach this job. So once I have my job set up, I'm going to position the PLR in front of the part. Laser cross must project on the flat surface, and we're going to create a reference image. That's what this teach-in is. So we configure the job for the interface. The robot's going to send a teach-in request, so I have a teach command, and we're going to reposition the PLR if needed. I've never actually had to do that on me. And then we're going to teach the robot how to pick the part. So once we've taught a reference image, we actually need to manually move the robot to teach the point that we want to use to pick the part up. So that will be our reference point that we're then going to use in a different frame when we're starting to move around. So I got a brush here. I apologize because this is not updating. Give it a moment. My device is having a slight issue here, a little technical difficulty. So I'm going to move this camera over so you guys can see what's going on here. Again, the idea here is to teach in. We're going to be using the PLR device to do that. So real quick, while I'm waiting for this to boot back up, there is a easy replacement feature on this device. So once we have set this up, if we do have an issue with the device, similar to anything I'm having right now, if you need to change it out, there is an SD card. That SD card is something that is automatically saved every time you make a change in the device. So what that means is it's an automatic backup. So if you need to change out the device, put a new device on, or if you need to even make a backup, you take the SD card out, you put in your computer, you back it up, or if you have a new device, you literally take the SD card out, you put the SD card into the new device, and it's ready to go. The only thing you really need to do is align it, nothing else. So that alignment, again, is a automated sort of setup, and you never have to really touch the robot. You just have to put the SD card in, you're good to go. So very good for maintenance capabilities and getting maintenance up to speed. All right, so get my device back up here. Again, I'm going to go to maintenance. I'm going to go to job here. All right, so I'm going to move to job 3. Job 3 does not have any data. It's going to load in job 3 here. And I'm going to press acquire to get a new reference image. So I'm going to leave my default exposure time alone here. Acquire an image, and this image is of the part I'm working with. If you see, it has made a X. It's automatically calculated that on my part here. I did not set up that tool. That tool is built in. So that's what this X is. From there, I need to use my brush tool to define the region of interest. So in this case, I'm just going to be using this. I have a nice, again, contrast here. I have good contrast with my white to black. I'm going to do that quick brush tool. It's going to create an edge sort of pattern here. And that's done automatically. Again, I'm not really doing anything other than brushing. It's already created it. The last things I need to look at down here are my reposition threshold and my max rotation. So it's reposition, again, is when do I want to say that I have too much rotation and I want to get a better accuracy measurement? Because if I'm a little tilted from the axis of the camera, I'm doing some calculations to alter my 2D image to then get my X, Y, and roll. If I'm dead on with the camera, then I'm getting a much better accuracy. So this is basically saying what do I want to allow? So if I turn it down, it's going to be dead on every time. If I turn it up, it might not work at all, and it might not ever reposition. Down here is my max rotation. So how much do I want to allow the part to rotate? That's a good way to error-proof your application if you have a tight space. So that's what those two are doing. So from here, all I have to do is teach this particular job. I'm not going to do that at this time because we don't have enough time to actually run through an actual teach point, but I'm going to show you guys what that looks like. When I go here to my teach program, my job number for my PLR is 1 because typically I'm using job 1 when I actually run the demo. U-frame 5 is my work frame for this rack. U-tool 3 is the tool center point for this these grippers. And then down here, you'll just see that I'm sending out a command for teach. So this is again, a Carol command. It just sends down to the Carol system. Carol processes that teach command, and it sends a whole bunch of data over to the PLR device. That will be the tool center point. It'll be the job number. It'll be any other sort of data that goes with that command. So we'll wait for a response, and then it will be good to go. So in this case, I'm not going to run it, but it would change this from teach to, okay, the job is taught, you're ready to go. That's really all it takes. So that's with my part positioned in front of the camera here. So if I'm ready to go on this side of things, the next thing I would do is I would, in my reference frame, take a point in order to pick up this part. So I would maneuver my robot, I'd go to the part and find a point where I want to pick it up. I would record that point in this reference frame. So in this case, it's reference frame 5. Once I have done that, I can back off and I can take a new image with the PLR, and then you're going to start using that matrix multiplication the same way we did with the alignment. And so then you go to your same point that you already took, but this time it's going to be in that multiplied frame, which for me is frame 7 in this case. So I would take my frame number 5 that I took my point in, multiply it by the offset from the PLR, and then maneuver in my frame 7 to that same point. So next thing to do here is we're going to go ahead and run this. Not really a whole lot more to it. So I'm going to take this, I'm going to put the robot into I'm going to run it slow at first, and then I'll put it into the high speed mode. All right, so the robot's going to recover because I had it down at that area. Now it's going to go ahead and run. So you should be able to see this robot's going to move up to the part. It's going to take an image. Image shows up on the screen. I did not have to reposition. Come down, pick up the part, and it's going to put it down on the other rack. Really this easy to set up. When I go on site, normally this takes 4 hours, 8 hours to set up. It's very simple. Again, purpose built. The goal is for it to be simple. It's simple for engineers. It's simple for maintenance. It has a very high uptime. We have several deployments of this, and that's what it's meant for. Deracking. So again, take an image. And in this case, I'm indexing forward just by a taught amount. I index forward 75 millimeters based on my part count. You could index forward based on where you last picked the part. You could index forward just based on a blind offset like me, or you could just always take it from the reference position. So if you see, it's going to go to the reference position, but this time it's going to be 180 millimeters forward of my reference position. Now take an image, pick up the part, do it again. So again, that is a majority of what we have going on here. Again, the other main feature here is in our micro SD card. Very easy to recover from any sort of issues with the device. So I thank you guys for your time. I hope it was valuable for you. And I'll open it up for question and answers here.
Thanks, Nick. Yes, we'll open up for questions now. Please type your questions into the chat section on the right-hand side of your screen, and we will get to as many as time allows. Nick, we have one question in here, and it came from way in the beginning of your presentation. You were talking about templates, and we had a customer ask, do you have templates for Nachi, N-A-C-H-I?
I believe we do not have Nachi at this time. It's something we can absolutely develop. We've developed, like I just finished developing the UR templates, so if it was something they're interested in, I have no problem developing the Nachi templates. We actually have quite a few relationships with Nachi that we could work with.
Awesome. Another question is, how does the PLR complement the work of factory employees?
Okay, so generally, I'm not exactly sure the details of the question here, but I'm going to go at it from the idea that how do factory employees benefit from the PLR? And yeah, so the PLR, the goal here is to limit people's repetitive motions. So it keeps them safer. You know, sheet metal, it can cut people, it can be heavy, it's big, it's cumbersome. You know, when the PLR, a big thing about it is you can reduce your need for precision racks. So for when you have precision racks, if one gets damaged, generally you don't know that until the robot's trying to pick a part out, and then it crashes into the rack or it bends apart, anything like that. And then factory workers have to remove this rack, put it in containment. There's a lot of work that goes into it. This helps them error-proof their job. It doesn't replace them or anything. This really helps them to be more efficient than anything else.
Great. Another question came in about the templates. Do you have a template program for Epson?
I don't believe so, but again, same answer. If there's interest, we will absolutely develop it. It generally takes me about 5 days to develop a template. It does not take very long.
Awesome. Another question is, does the software have a name? Is it specific to SICK?
Yes, so this is PLR, so Part Localization Rack. It is proprietary to SICK. It's part of our app space. So app space is, we have basically a programmable camera, and we have a lot of different apps you can run on that camera. In this case, PLR is one of those apps.
Great. Those are all the questions we have received. Is there anything else, Nick, you'd like to mention?
I mean, I hope you guys enjoyed it. I hope that there's some applications that we can help you guys solve. This is a pretty powerful tool, and if you're looking for something else, whether it's bin picking, if it's 2D robot guidance, we have a lot of products for those as well. So please get in touch, and we'll definitely help you out.
Thanks again, Nick. And we hope to see your listeners again soon. Please visit sick.com to stay in touch with our upcoming webinars and events. Have a great day, and thanks again, Nick.